Welcome to number 4 about light and waves, the nature of light as a wave. Newton. This is one of the few times Newton got things wrong. So Newton suggested a particle model for light. This was opposed by Robert Hooke and Christian Huygens. And they believed in a wave model for light. Obviously neither is right. Because today we know, I hope I wrote no correctly, that light is best described by a combination of the models. Okay, moving on. Huygens principle. Just very simple. Each part of a wave acts as a new wave source. Okay, now what we're going to do in a bit more detail, refraction. We basically know about refraction. So this is the bending of light as it passes from one medium to another. Now we're getting into stuff we haven't heard of before. Each medium has a refractive index. Which is a measure of the speed of light compared to C. So N equals C over V, where N is the refractive index. Right, diagrams. There's some edges and surfaces and all sorts of stuff. So, air one side, glass the other side. Everything is measured from a thing we call the normal. And we know what a normal is, because a normal is at right angles. So Everything is measured from the normal, not from the surface. Okay. Let's have some nice pink light. Theta 1, theta 2. So glass will have N glass, air will have N air, but N air equals 1. Refractive index of glass is 1. Now in terms of mediums, less dense, more dense, fast, slow. So because we're going from less to more, light bends towards the normal. I'll get my diagram on the screen. So now we have a thing called Snell's law. Snell's law is really simple. N1 sine theta 1 equals N2 sine theta 2. You can complicate it and get a thing called a relative refractive index, but it's not used very often these days. So, relative refractive index. Okay. Second half. Different concept called total internal reflection. So when going from a more dense to a less dense medium, the light bends away from the normal. This means there is an angle of incidence where the refracted beam passes along the surface. This is the critical angle. And beyond the critical angle, everything is reflected. Beyond the critical angle, all light is internally reflected. Okay. So, let's set up a similar one to before. Plastic, air, N equals 1.0, N equals 1.4. We put in our normal, and in theory, well not in theory, in practice, there is such an angle called theta C, where, and that's meant to be along the surface, where, so theta 2 equals 90, where the refracted beam goes straight along the surface. So going back to basics of Snell's law, n1 sine theta 1 equals n2 sine theta 2. And put it in perspective for this one, 1.4 sine theta C equals 1 by 1, because sine of 90 is 1. Grab a calculator and finish that one off. .6 degrees. We'll talk about the fine details about this as we get there. Alright, last thing for this video, thing called dispersion. And dispersion's not complicated, it's just based on all frequencies do different things. So all frequencies refract at different angles, and bending increases with frequency. We will attempt to do a bit of a diagram of that with a prism. We'll even do the light coming in as black because I don't want to use any of the colours. But white light, it actually does split a bit inside, of course, but then when it comes out, I don't have any violet, so we'll just draw what colours we have. So, blue, green, yellow, in theory orange and red. I don't have the right textures for all the rest. And obviously I exaggerated the bend because they do all bend. But different frequencies bend different amounts, and that's what we call dispersion. Okay, that's the finish of this one.